Okay, welcome everyone. How's everybody doing? Staying safe? Mentally well? Time of a semester where we maybe experience some burnout, some stress from other things, but just remember, it's all little stuff. All we got to do, there's a country song I love. It's all you got to do is breathe. I don't know, something. All we got to do is live and die, and I'm in a hurry, and I don't know why, something like that, So, yeah, life makes us in too much of a hurry to get someplace. Don't take the time to enjoy where we're at right now. So, where we are right now is kind of a nice opportunity to assess your learning, give this opportunity to get a nice strong score on the second part, hopefully. So we're going to go over, we have all these sections that we've covered, so the test will just be 11.4 to 11.5. There is this extra credit for 12.6. Got an email from the coordinator just to remind everybody that 12.6 elasticity is not on the exam, and it is not on the final exam. She gave us the authority. We can either throw it out, not even touch it if we don't want, make it extra credit, and I figured it's good as an extra credit. It's not too hard to do, so if you go into that module, there is a video lecture, there's a formula, you sort of plug it in, and if you've done economics, they have this thing called elasticity. This is the application of it, so this is math of it. So it's kind of good, but it will be available to you all the way through the end of finals week. So if you want to do it as a last-ditch effort to boost a little bit of a score, again, the points won't make a huge difference, but they make a little bit, every little thing. So because it will be completely extra. It'll be those extra 10.5 points when it does come over. Secondly, preparing for the final or for the exam 2, there is this link down here, test 2 review, most current. That's what we're going to kind of work through a little bit today. I've got a slideshow where we're going to review section by section, just a real brief review, and we'll throw in a few examples. The first link, exam 2, section 11.4 to 11.5, summary and solution videos. I just want to highlight this again. When you come into here, there is a review for each of the sections. And I'll show you. And for each section, there is a PDF, which I saved basically when I was making the video. I had a PowerPoint like I usually have. I saved all the stuff in there so you could just look at the PDF, see it all written out. There's no explanation or anything, but sometimes that's the better way to do it. You can see the whole picture. Otherwise, you can watch the video, which they basically contain the same things, but the videos will take anywhere from 20 to 30 minutes. I think there's one in here that's almost 50 minutes. But again, what I do is I try to make a real brief review of the concept. I don't teach you the concept, just to remind you, and then I start working through all the examples from the exam 2 review. It was done a previous semester. I've compared the 2 reviews, and there's only a couple questions that were on the old review that are not on the new review, but they're still good ones to practice. I only found, I think, 2 of them that I was able to identify that are on the new review that weren't on here. So, but there's enough examples in here, so we're going to go with that. A couple of those that weren't on, I think I've got into today's reviews as examples. But you can come in here, take a look at any of the sections you've done that you struggled with, get a little bit of a quick overview, and then get into the examples, okay, the review questions. And again, at this point, probably the best thing to start doing is getting into that review. With that in mind, I'm going to push the due dates for the homework until next weekend so that they aren't a pressure. And sometimes that helps, is if when I'm pressured, I don't get as much done because in fact, sometimes, a couple reasons, I may have lost some jobs, but my boss starts getting on me to go faster, I go slower purposely. I know this about myself. little bit of a jerk that way, but hey, you want to push me, I'll show you how slow I can go. But so that's why sometimes you take the pressure off. I'll get more done if I don't have pressure on me. So that's what I do is you have plenty of time to do the homework. I think it's valuable to get as much of it done as you can to prepare for the test, but I want you to do it in that manner, not thinking, oh, I got to get this stuff done. Think of, I got to learn this stuff so I can do well on the test. So those will be pushed off. So a good time to start focusing on the review. The other piece of advice I have for you is that also spend some time reviewing the parts that you already understand well, and celebrate that you understand those well. Work those questions again and say, yeah, I got this. This part I'm going to do well on, and I'm going to practice a little. Yeah, I'm really good at this. That'll build up your confidence, so when you get to the parts that are not as clear to you and you're struggling, you don't get that internal talking to yourself of, I just don't know what I'm doing. You've got this, no, I do know what I'm doing on this. I'm struggling with this. So the importance of building that personal confidence on the things you do know. Okay, even if it's only one thing, focus on that one thing and say, okay, I know this one thing. Because I'll hear sometimes students say, I don't understand anything, and I'll go, no, actually you probably understand 90%. It's these little things that you're focusing on that make you feel like you don't understand anything. So that's an important thing. Then secondly, there's this middle thing, test 2, WebAssign review solutions. We don't use that activity anymore, and it's maybe been 2 years, but they used to have a WebAssign with 40 questions as a review. They stopped doing that, but that semester I taught it, I did videos where I did all those solutions, so they might be of help to you. And I did it, I think, by groups of 10, so you'll see question 1 through 10 and then 11 through 20, so groups of 10. You might look through there, and there might be some of the homework in there, type questions that might be helpful. Okay, so it's there as a resource, but again, you don't have to. Again, the thing is sometimes when you get too many resources, where do you focus? Again, what we're going to want to do is sort of start with this most current one. There's the PDF at the top. And again, what I've done is I've done some screenshots, and in the summary I'm going to do today, we will do some of these, but I don't have it worked completely through. You'll see that in that first module I told you about with the section by section review. There is also this PDF, which is an answer key, and sometimes they provide some good explanations, sometimes they just provide the answers, but those are good. That's a good thing to work through. Okay. And I just got hammered with some other things, so I haven't got a good sort of quiz thing. So we'll do the same thing to get the credit for the quizzes what I'm counting as a quiz is work through these reviews. Again, the more you do, the better you'll do on the test. I haven't, again, just take a snapshot that you did some work. I'll have a assignment, you upload it. I'm not, as long as there's something uploaded, I'll give you the points. I'm not going to go through and assess, did you work enough problems, or did, just do some. And again, it's sort of like participation points is the way I look at it, that you at least did something, okay? But do the review you need to do well. So with that in mind, let's go ahead, and I've got the slide deck that will kind of guide us through each of the sections, and we'll work a few examples just to see what's in there, and I'll also highlight a few things that won't be on the test specifically, so that you won't have to worry about it. Okay, so any questions or concerns about the exam or about where we're at before we start into this? And then, because yesterday I forgot to explain, the exam's very similar to the last one. There are 6 multiple choice questions at the beginning. Question 7 is a true-false series. I think there's 4 or 5 of them, true-false in there. And then there are 5 open answer type questions where you show your work and you just, do that kind of thing. Secondly, I'll maybe announce it at the test, but try to put your put the work you want me to see on the exams rather than on some scratch paper separately, because those are a little bit harder. But anyway, we'll go through that. So here we are. We started off this section with the chain rule. Now, the stuff from test 1 will not be directly tested on here. However, as we saw with the chain rule, some of the chain rule does require us also to apply the product rule. Could require the quotient rule, but that's not going to be tested directly, and we won't, I'll just let you know, we won't be, I don't remember seeing anything with the quotient rule. So but the product rule is built into some of the things we're going to need to be doing. So again, we don't test directly on it, but we still need some of these earlier skills we have. So we start off with what is the chain rule. The chain rule, I keep forgetting to start my toolbar because it gets in the way. Here we go. Okay. So the main thing with the chain rule is to be able to identify that there's a function inside a function within a function. So there's an outside part and an inside part. And so when we take its derivative, and again, we could do it in either order, but we're going to take two derivatives, a derivative of the outside part, and then we're going to multiply that times the derivative of the inside part. So I'll just do this here. The outside part, the exponent comes down, so we get 3. The stuff inside the parentheses does not change. And then we subtract 1 from the exponent. That's taking its derivative, right? That's the outside part. And then the second step is taking the derivative of the inside part. And the nice thing is when we do it this way, the inside part's sitting right here. We could just look here, okay, 2 times 2 is 4. 2 minus 1 on the exponent is going to give us x to the 1 power. And then the second term, derivative of x, is just 1. And now we're done. Okay, so that's a chain rule. We're going to just identify the interior part, exterior part, take its derivative, and go through. And I've got it kind of laid out here. So I did this thing with I cubed, inner part cubed. So we take the outside part times the derivative of the inside part. And again, there's some notation, but for me, the notation always seemed to be more confusing than anything else. Okay, so let's take a look at this example, and this one does come from the exam review. Looking at it, it kind of looks like maybe a quotient rule thing, right? Because we've got this function down here, but we've got a constant in the numerator. So just to give you that sometimes if we do a little algebra in advance, it'll make the calculus easier. So any suggestions on what we should do algebraically to make this easier to take its derivative?
You can bring the bottom stuff up and then change the 4 to -4.
Perfect. So this becomes 25 times x squared plus x plus 2 -4. Good. Call the elevator rule, or right, put it up in the numerator. So that now we're not worried about quotient rule or anything, but we do have to have the chain rule. So in this one, the 25 is not a function, so we don't have a product rule here. 25 is just a constant multiplier. And remember, constant multipliers, any constants, just tag along for the ride. So I'm going to put my 25 there. When I go to take this derivative, the outside part is the -4 exponent, so that's going to come down in front. So I'm going to have 25 times -4. The inside does not change. X squared plus x plus 2. And then I subtract 1 from the exponent, so -4 minus 1 is going to give us -5. That's the outside of the function, halfway done. And then I'm going to multiply times the derivative of the inside stuff, and notice it's right here. So I'm going to I'm going to keep my focus right there. It's that derivative of the inside stuff, which is going to be x squared. Its derivative is 2x to the first power, plus the derivative of x is 1, and then the derivative of 2 is 0. So that's sort of our answer. We can, let's take 25 times negative 4. So we're going to have negative 100 here. X squared plus x plus 2 to the negative 5. 2x plus 1. And we're fine to leave it there. Do recognize that this negative 5 could be put back down in the denominator and become a positive 5. If it's a multiple choice answer thing, you might see it that way. You could leave the, you could do the answer. What I do is I'll take either one. So if you've got this as a step, like on the last one, sometimes the algebra would fall apart and you'd actually make errors. I don't count those errors. If I saw a correct place where you could have stopped, I'll circle that and say, yeah, that was, you get full points for that. Maybe you made some algebra errors. But you could also do the algebra, and that's fine too. You know, you could distribute the 100 over here, but this is perfectly fine. I sort of would do this as well, just because it's there, you know, the 25 times negative 4, but you should, you know, at least finish up the math. It looks a little prettier to go ahead and do the simple arithmetic. Okay, but the main thing I'm looking for when I assess something like this on an open is that you know how to take the derivative. That's what we're getting on. Okay, questions on, so that was 11.4, and there's other ones to practice. Again, chain rule. Okay, we use the chain rule extensively in 11.5, so we, even though it's not specifically in here, because of the nature of logarithmic and exponential functions, that they often have a function inside them. Logarithms have it inside the logarithm, exponentials have it up in the exponent. We oftentimes will end up using the chain rule on these. Okay. Also, with these two functions, we have a different way of taking its derivative than we've been doing. So far, you know, we had exponents, bring the exponent down, subtract 1. That does not apply to logarithms and exponentials. So remember, for a logarithm, if we're just taking the natural log of x, and we don't get in, the test doesn't have anything specific about absolute value. Some of the questions did, but all that absolute value there is defining the sort of the domain, because you can't put negative numbers into a logarithm. Just kind of ignore them. Just go ahead and take its derivative, and you'll be fine. So don't worry about absolute values. They're just kind of there to define the function. But when we take this derivative, so the derivative of natural log, it's going to be just 1 over x, right? The logarithm goes away when we take the derivative. And it's not really, I've seen proofs for this, mathematical proofs. It's like 2 pages. I barely understand. There's some tricky stuff it does in the middle. So it's not even a smooth flowing, from a mathematician's point of view, smooth flowing proof. And it doesn't really help in understanding it. Just, so it's best for us to just say, that's what it is. It is, you know, why is your name Mike? Well, that's because that's what my parents called me. So, you know, it is because it is. I don't always go by Mike. Sometimes I've got nicknames and stuff. So anyway, but this is, it just is because it is. So when we come to take this derivative, again, the outside function is going to, whatever's inside these parentheses, it's 1, the derivative is just 1 over that whole stuff. That is the outside derivative. And again, we're halfway there. The second part is using the chain rule. We've got to multiply by the derivative of this inside stuff. Now just be careful, we're multiplying by it, so it actually goes up in the numerator. So you'll see the stuff in the denominator was everything inside the logarithm. The stuff in the numerator is going to be the derivative. So again, we can focus right down here. It's 3 times 5 is 15. Subtract 1 from the exponent. 3 minus 1 is 2. We come to x squared, the 2 comes down, subtract 1 from the exponent, that's 2x to the 1 power, and then we take the derivative of 4, which is a constant, so that's 0. That's perfectly fine. Beautiful. If you want, you may see this again with this, the derivative of the inside stuff up in the numerator and the stuff from the denominator down here. Either one is acceptable for me on an open answer type question. Just be prepared, you could see either one of these in a multiple choice. And probably in a multiple choice, they'll list it that way as a fraction. Okay, so see, it's got that chain rule in, but just anything with the natural log, 1 over that. Questions? Okay. Exponentials, again, very simple. They are their own derivative. But that simplicity makes them sometimes the harder ones to work with, because it just doesn't feel like we're doing anything with that derivative. So when I take the derivative of something like this, the derivative of the outside part is simply ex squared plus 1. What you might do is, I like to put parentheses around this, so this tells me that is the inner part of the function, right? The exponent is the inside. And sometimes it helps me if I put parentheses and say, okay, that's that. But the outside derivative, you just copy it over. It's its own derivative. E is, okay? And then just remember chain rule. Now we've got to multiply by the derivative of the exponent. So the derivative of x squared is 2x to the 1 power. Derivative of 1 is 0, so plus 0. We don't have to write that. So there we are. Again, you'll oftentimes see this. They'll put the inner derivative first, because e, with these exponents, so it doesn't get all mangled up, they might write it as 2x e to the x squared plus 1. And that's fine. Either one is acceptable. Okay, so just remember, with exponentials, we're going to have to apply that chain rule. And there we go. And e is its own derivative. Notice I haven't done anything with a base other than e, or a logarithm that has some other base than the natural log. On the exam, we're just focused, those are the two you'll need to know. Okay. Doesn't hurt. You could know the other ones, but these are what we're going to have you focus on. So far, so good. First 2 sections. Again, just bringing you back that there's going to be some questions on there. Again, look at the review, figure out what goes well. Then we did 11.6, implicit differentiation, and this was sort of the last of the real differentiation rules, because this was, we learned how to take derivatives of things that have more than one variable, 2 variables specifically. So we were working on something like this, and basically the only thing that made this different is since we have 2 variables, we have to sort of distinguish which is the main variable. And so typically what we would choose is that x is our main variable, so we take the derivative of x with respect to x. We usually don't write this because dx over dx is just 1. But when we take the derivative of y, we would always write that we're taking the derivative of y with respect to x. Okay, so that's a marker saying that this rate is how y is changing, but x is our sort of our main tracking thing. Okay, so we use these sort of things, and so this one's fairly simplistic. There's no product rule in here, so I thought I would do this one first. So in this case, we take the derivative of everything, term by term. We're going to even take the derivative of the 0. So the derivative of y to the 5th, just think of it as a variable, y to the 5th. Well, what happens? The 5 comes down, so we're going to get 5y, subtract 1 from the exponent. That's going to give us 4. And that since it's a y that we're taking the derivative of, we put this marker that we took the derivative of y with respect to x. And in the end, that's what we're going to solve for, right? That's what we're looking for. We go to the next term. Derivative of y is 1. 1 times y to the 0 if you want, but y to the 0 is 1, so it's 1. And then we put the marker that we took the derivative of y with respect to x. Finally, we get to the last term, derivative of x. Derivative of x is 1 times x to the 0, which is 1. We could put this marker dx over dx, but that's just 1, so it's just kind of cleaner if I don't put that, but I don't have to. And then on the other side, I take the derivative of 0. If this was any other number, I would take that derivative. If it was a variable, I'd take its derivative. Yeah, so derivative, but what's the derivative of 0? It's still 0. Any number, any constant, the derivative is 0. And remember, that's because constants would have are a horizontal line, so they have a slope of 0. That's where that comes from. Now, in this, the whole goal was to solve for the derivative of dy dx. So we see that we're going to need to factor those into 1 dy dx. So that was all the trick. Anything that doesn't have a dy dx, we're going to get to the other side. So it's kind of like get it to safety. And so I'll do it in this way. Plus 1 minus 1, that's 0. 0 minus 1 is going to give us a negative 1 over here. And I'm going to do in the same step, I'm going to factor out the dy dx. So those kind of get factored to the back. And what's left, that got out of there, so I've got a 5y to the 4th. And this is where it's helpful to put this plus, this 1, even though we didn't have to, but that's what's left here when we factor it out. Okay. What I'll tell you to do is also go back at least and mentally redistribute that dy dx and see that you get what was on the previous step. That will help your mind, because your mind's going, this is weird, because we spend all our school years distributing, but we don't do as much factoring like this, and it's just, I remember it took a while for this to kind of click. When it clicked, I go, well, I couldn't understand why I had so much problems with it, but I did. And I think it was when it was that mental thing of it's not something we're usually going the other way. And this factoring of something that's so complicated like that, it puts a stress on our brain. So if you distribute back a lot of time, and I think that was the technique I would use. I would do, oh yeah, it's just this in this form. So then the last step to solve is we take what's ever in front of the dy dx, because that's multiplying, and we divide it on both sides so that that cancels. And then our derivative is negative 1 over 5y to the 4th plus 1. Right, and I cancel, that's a 1. So there's our final answer. Okay, so that's the, what did we call this? I forgot what it's called. Implicit derivatives. Kind of a weird name, but multiple variables. So far, so good? Okay. What I'm going to do is I'm going to jump to what we just did on Tuesday, related rates, because this is directly related to implicit derivatives. We're going to use the implicit derivatives in this thing. And all that's new is that we've actually going to have 3 variables now. We'll have maybe an x and a y, but we'll also have everything is changing over time. Everything's changing over time. So that remember that variable for time doesn't show up in the formulas. However, it's sort of understood to be there. Okay, so I'm going to go back to this. This is one we worked extensively, but I'll let you know on the exam you will be given you'll be given the equation just like they're giving us here. Okay, and so the ways to do these related rate problems is, you realize that the related rates is that we start with the formula. And again, I haven't even read over it yet, but it's volume of a sphere. Okay, so it's this round thing, and this is the formula that gives us volume of the sphere. The first step is to take the derivative, because that puts it in motion, right? Derivatives are rate. right now it doesn't include time in this. It's a static function. It's algebra. But by taking the derivative, we actually set it in motion. We bring in the construct of time. So think of v as just a variable. It's like x to the first power. Take its derivative. That's going to be 1, right, times v to the 0 power, but which is 1, dv dt. So it's how volume is changing over time. That's what this derivative that we just took. Okay, implicit derivatives. On the other side, we've got 4/3 and we have pi. Those are numbers. Those are constant multipliers. They just tag along for the ride. The r is a variable, so we take its derivative, r to the third. The 3 comes down, so let me change colors. All right, and we'll just put it in the very front, so we're going to multiply by 3. We'll simplify this stuff. And then I subtract 1 from the exponent, so I'm going to get r to the second power. But remember, this is implicit derivatives. I also have to put the marker that I took the derivative of r with respect to time. Okay, and again, yeah, clean this up. 3 divided by 3 is 1. And then now is the time I go back. So after I take that derivative, that's when I go back to the question and I try to plug in the information that they gave me. How do I identify the numbers that are derivatives? We see words like rate, right? A derivative is a rate of change. We see words like per in the units, centimeters per second. That's a rate, right? That's a fraction. This 15 cubic centimeters per second, that's a derivative. And let's see which kind of which one is. Assuming the balloon is filled with helium, the internal part of a balloon, that's what we call volume, right? There's a radius in there, but what's getting filled, that's the volume. This 15 is the dV dt, okay? We have another number here, and again, 3 centimeters. What is lacking from this unit? It doesn't have a per. This 3 centimeters is not a derivative, okay? And that I just kind of emphasize this because I'm working with a few of you. That was one of the problems you were having, is identifying the numbers, which ones are derivatives and which ones are not derivatives. You know, what goes where. This is the radius at a particular time. This is a value of r. It is not a derivative, okay? So that means for the r squared, I'm going to put 3 in for r. So, and the thing is so, okay, I've got a dv dt, that's sort of a variable. I know what that's going to be. I know what r is. They don't tell me about dr dt, but the question is, how fast is the radius growing? The question is about what is the derivative of the radius. That's what the question is. So you'll see that you'll have numbers for every one of your variables except for one. That's the one that you don't have is what the question is. Okay, so that's kind of a good way to do it. So dV dt is 15. Again, you could put the units in there, but I find sometimes they get in the way. 1 times 15 is still 15, so I'm just cleaning up as I go. The 3's got canceled, so then I've got 4 pi. R we figured out was 3, so this is going to be 3 squared. I plug that in. And dr dt, I don't know what that is. That's what I'm looking for. That's what I'm solving for. So now I've got everything cleaned up, and the rest of this is arithmetic and algebra, right? So 3 squared is 9. 9 times 4 is 36. So I could write this as 36 pi. And then I divide both sides by 36 pi. So I get dr dt equals 15 divided by 36 pi. I'm going to put a little parentheses here because if you put it into your calculator as 15 divided by 36 pi, you might get a wrong answer because it might take 15 divided by 36 and then multiply by pi, I think is what it does, when you actually need to take 36 times pi first and divide by that whole thing. So order of operations sometimes makes a difference. And again, this one's saying they want it to 2 decimal places, so plug it in the calculator and get a result. Get a decimal. So let's go ahead and do that. 15 divided by, and again, I'll put the parentheses 36 pi. I'll use the pi button because that gives me, rather than 3.14. And I get 0.1326. And again, they want it to 2 decimal places, so my final answer would be 1.3. And again, if you put 1.13626, it's more accurate. If it's a fill in the blank or open answer, that's going to be fine. But just, if it's multiple choice, you'll probably see the 0.13. And again, you could put units on it because, right, it is the radius changing over time. So that's going to be centimeters per second, right, because it's over time. Centimeters per second if you want. But that's all good. Okay, so that's the application part of the implicit derivative. I'll let you know there is one, just to get you thinking of this, there is a multiple choice one that's set up like this, and you don't go for the answer, you go for what are you going to set up. So it's a little bit wordy, but you might want to just not look at all the answers, go through these steps, and then match your answer with how you got it set up with all the 4 or 5 choices. Okay, because otherwise you get reading. If I just look at, okay, here's the question, I start reading the list, they all look good. They all sort of seem good until I go off and work it on the side and I say, okay, this one's wrong because how multiple choice are. They'll have 3 parts to it and 2 of them are right and 1 of them is wrong. And so it's just a strategy. When you've got a multiple choice that has wordy multiple choice answers, go ahead and do a little bit of the work. You don't have to get the answer because that's not going to be there, but at least get it set up without looking at all those things. Because again, when I do it, and I've got experience doing all this because I teach this class many times, and it will get me off track. And I'll find, it's this one. Oh wait, no, it's not. That's part's wrong. And so anyway, just a strategy, give you some advance notice. I don't think, I didn't tell you exactly what the question was, but it will help you prepare for the strategy that you need to use on some of these. Also, there are some in there where they give you the function, they'll put a letter and they'll tell you that letter is a constant, like they'll put an A or a B. Treat it as a number, as if it were a number, okay? And look for that. It'll say A is a constant, which means it's a number, okay? It's not a variable. So, but that I've seen that little piece will throw you off because most of the times we don't do that. And for some reason, they decide to throw these sort of tricky ones to see if you catch it. For them, it's simple, but it's not. You think it's this A, because you see a letter, you think of it as a variable. Typically, what's supposed to happen, that's the problem with math, is it's not as consistent as it should be. But when you have letters at the beginning of the alphabet, A, B, C, D, those are supposed to be constants. They're unknown constants. They're not variables. The variables are supposed to come from the end of the alphabet, X, Y, Z, T. So that's how it's supposed to work. So just watch for that as well. There's at least one. I think there's only one of them that does that, but it throws that in there, and I don't want it throwing you off. That A, and it says it's a constant, so just treat it as if it were a number. Minimum and maximum. So this section was really a skill-based thing, wasn't really problem solving. We were either given some graphs or we're given some functions. We're typically given endpoints, and we want to find all the maximums and minimums, so the high points and the low points. You can do this by simply go ahead and graph it. Even if you have to show your work, a graph will taking a look at it, you'll see where the high points and the low points, and a lot of times it just, everything else will flow out of there. I'm going to do it without the graph first, but we'll come back to the graph and I'll say how it is. So with these ones, find the exact location of all the extreme and absolute extrema, a relative and absolute extrema of the function. So the minimums and the maximums. We're always going to check the endpoints. So this is an interval going from x equals -2 to +2. So I know I need to check the endpoints. So I'm going to look for what is g of -2 and what is g of +2. So those will be two endpoints, right? And then the only place that a minimum or maximum can occur interior to that is a place where I got either a mountain or a valley, right? Mountains will give me maximums, valleys will give me minimums. And those occur wherever I get a horizontal tangent line, which means the derivative is going to be 0. Okay, so I'll find where those are. We're not going to get to the tricky ones where the derivative's undefined and there's some sharp point. Those you can only find by graphing anyway, but we're not going to throw those on the test. The interior points here will be where the derivative equals 0. So what we want to see on these in the open answer is that you do take the derivative of the function. So again, we're going to do this. I'm going to use the technology to do this though. So we want to see the derivative. 3 times 4 is 12. Subtract 1 from the 3, we get x to the second power. We bring the 1 down and we get -12. Subtract 1, we get x to the 0, which is 1. And then the derivative of 6 is 0. So this is our derivative. We take that derivative and we want to find where is this derivative equal to 0, because that gives us a horizontal tangent line that will identify either a maximum or a minimum, right? Because that's only two places we get horizontal tangent lines. Again, you could graph this, or you could say, okay, let's divide everything by 12. That might make it easier. So then I have x squared minus 1 equals 0. I could add 1 to both sides. I could factor it too, and then I could take the square root of both sides. Just remember, when I take the square root, I get both a positive and a negative answer. So this gives us that x is equal to either -1 or +1. You can kind of see that either one would work. So those are two places where the derivative is equal to 0. I'm going to check those. And again, I'll show you, when you look at the graph, you might have picked these off of the graph. But again, if this is a show your work type thing, we want to see that you know to take the derivative equal to 0. Backtrack, so you might find these first by looking at the graph, but then also come back and do the derivative. Okay, and now we just need to find out what these values are. The way I like to do this the best, we can plug them into the function, right? But then you're going to have to cube it, multiply by 4, do this. So what I like to do, because I'm going to do this anyway, is I'm going to look at the graph. I want to see the graph, so I'm going to go to my graphing calculator. Where's my graphing calculator? It's over here. Hopefully it opens up relatively quickly. Not. What time is it? Yeah, we're almost there as far as time. Here it comes. We'll be done in maybe, actually there's this, and then there's one more thing. Yeah, so we'll be done in 5 or 10 minutes. And actually, I did this yesterday, so it's actually already graphed. So just to show you, 4x to the third minus 12x plus 6. If we look at the graph, what I did is on the window, I'll just show you, I put the x minimum at -2 and the x maximum at 2, so I've got my endpoints. I'm not looking at extraneous stuff. I kind of figured out what the y's needed to be so I could see the graph. So I can see, oh yeah, here's -1, there's a maximum, negative or +1, there's a minimum, here's a maximum, here's this. And then what I can do is if I go to the table, so I go second graph, and in the table I can pick out these values. -2 is -2, -1 is 14, and then the other 2 points I wanted was 1 and 2. 1 is -2 and 2 is 14. So I just picked them up. Those are plugging those into the function for me. But if I do that, again, especially in testing environments, I'm going to be stressed out already. I might make some arithmetic errors. If I put it in this way, I'm less likely to make those errors because I carefully look at that I got things in there. So when I come back to, let's just go back to the slideshow. Hopefully, oh shoot, I deleted everything. I thought I chose the other one. Anyway, so we had g of -2 here. We figured out g of -1. So I've just got them in order. And this we saw was -2. This we saw was 14. This was -2. And this was 14 from the calculator, right? And I don't have to show the arithmetic. When we say show your work, you don't have to show that 2 + 2 = 4. No. Okay, so calculators are good for that. If you wanted to show that you use the graph as well, again, over here we had our derivative part, right? We took the derivative and we showed all our work on that. That's fine. If you wanted to, you could show, I gotta see, how was this? This was something like that, something. A quick little graph. That doesn't hurt. But now we've got to label these. And again, the best way I see to label it is if I look at the graph, it's a little bit clearer to me that this -2, that there was 2 places -2, that those both are absolute minimums, right? Now, we talked about that there can only be one absolute minimum. Well, there's only one absolute minimum value of a -2. However, 2 points, it happens at 2 places, right? They both go down to this. So these both here are absolute minimums. If one of these was, say, like at -1, then that would have been a relative minimum, and the other would be an absolute minimum. So just kind of go through there. And then we've got 2 places where we have the same absolute maximum value of 14. So both of these end up being absolute maximums. So we identify them as such. Okay, but again, you'll have a question on there, give you your endpoints, check your endpoints, check the internal places where the derivative equals 0. Those are possibilities. Use your graphing calculator to look at the table to do the arithmetic part for you, and then just identify the place and where they are. Okay, so a question like that. So far, so good? Okay. And then our last section, no, we got 2 more. Applications of max and min. What I'll let you know on here, this is where there was like more problem solving and building fences and rectangles and triangles and stuff. We're not going to test you on geometry. We're going to use business-related functions, okay, for this particular one. So this is the one that had the problem solving. So we'll go for something along these lines. So I want to help you. If you look back to that lecture we did, focus on the questions that dealt with the setting up of the business type functions that involved profit, revenue, costs. Okay, don't worry about the building fences around a river type ones. Don't worry about that one with the girth of the box. Those are all geometry type problems. Those are not going to be on there. Don't waste your time on them. Again, maybe if you need to do that homework, do that after the test, but for the test, ignore them. Okay, focus on these. So one thing I want to highlight is, so this is directly from the review. Worldwide annual sale of a product were projected to be approximately this. So this Q is quantity of the amount sold, right, in millions of units. P is the dollars per unit. So that's the price. So, and again, if you've taken some economics, you know the supply and demand, and the more demand, the more volume that you have available, typically the price will be lower that you're able to get. Or, and if you if you charge a lower price, you'll sell more. If you charge a higher price, you might sell less. All that kind of stuff. Of course, unless you're like name brand stuff, they seem to sell more the more they charge, because they make it seem like it's rare. All that kind of stuff. But what selling price would have resulted in the largest projected annual revenue? So let's think how we get revenue. This is the important thing in setting up, since they want revenue, because oftentimes revenue, we confuse it with profit. Revenue is just the money that's going to come in. So if I have selling my newspapers at 50 cents a paper, and I sell 10 of them, what was my revenue? 10 times 50 cents, right? I made $5 of revenue came into me, because that's what I'm selling each one to. Revenue is always the price times the amount sold. Okay, so we know what is the price. Price is just P. What was the amount sold? Q. And so it's going to be a function of P. So revenue in terms of P, and then Q is this function up here. That's why they gave us this other one, minus 10P plus 4220. Okay, so just see that revenue is going to be price times quantity. And sometimes the price function itself it could be more involved. Depends on how, because sometimes the price we're able to set depends on how many we were able to make. Sometimes it depends on other things, but think of it just price times quantity. In this case, the quantity is a full function. We change the price, we'll change how many we sell. And then we distribute this, right? So this is a little bit more natural, and we see that we've got a function P squared plus 420P. It's quadratic. Again, we could graph this, a quadratic, and it's got a negative leading coefficient, so it's going to be concave down. It will have a maximum. We just need to find that vertex if you want. Or, with the use of calculus, we want to find the place where the first derivative equals 0, right? So again, that's what we want to see, is that you use your calculus skills, take the derivative. 2 times 10 is going to give us negative 20. P to the first power plus 4,220. We're going to set this equal to 0, solve for P, and that will give us the answer for the price, right? What's the largest projected annual? So what's selling price? So that's the first question. So we're going to get P equals, subtract 4,220 and then divide by negative 20. So this one is going to lead us that P would be equal to negative 4220 divided by negative 20, which is 211. The B part, though, what would be the resulting revenue? Be careful here. Remember, the revenue is the function before we took the derivative. The derivative is a rate. It's a marginal revenue. It's the revenue we would make by getting one more. We want to find what is the total revenue. So we go back to the original and we plug in our price of 211, and we're going to use this function here. Not the derivative, but this function. And again, when I emphasize things, I remember, because I took calculus twice. And I remember the first time I didn't do so well. Second time I did much better because I had a dyslexic professor who thought the same way I did. But so I remember how I started to understand this stuff, and I remember where the problems were. And I was the guy who would plug that back into the derivative function, I get it wrong because I put it in the wrong function. I was doing sort of the right thing, but in the wrong place. So, and again, you could plug it in, you get the answer, but that's what you're going to need to be able to do. I encourage you to go back to the homework, to the lecture I had. I went over these particular, because I just copied them over. These are, this top one is just like the one we just worked. It was in the homework as well. And again, this one wants the greatest revenue. So it's exactly like it. And there's, in the lecture video, I worked through it. This one is good to go over because it's similar, but in this one, they want profit, right? So we go through this one, and remember, profit is revenue minus the cost, and revenue is price times quantity. So that all fits in there. Again, we've worked through this, so take a look at that. It's just some good additional practice. Okay, look at both of those. And if nothing else, just watch the solution process. If it makes sense, great. But just remember, if you're like me, if you're sitting in the passenger seat, oh yeah, I remember how to get to Grandma's house. But when you're in the driver's seat, it's always different, right? You forget to make that little turn here, and then all of a sudden you're lost. So it's okay to watch from the passenger seat, but get yourself in that driver's seat at least a few times. Test it out. Do the test drive. All right. This is our last section on concavity. There's two concepts we want you to take out of here. One has to do specifically with what the second derivative physically means. And again, it's not a direct business application, but it's really the only physical representation of what the second derivative is. If we have a position function, that means if something's moving and we know how far it's moved, that's distance. If we take its derivative, we've got the speed it changed. So that's, you know, that's you're driving your car at 55 miles per hour. That's your speed. Velocity is just directed speed, so which direction you're going into. And then the second derivative is the acceleration. It's how the speed is changing, whether you're speeding up or slowing down. So acceleration is that feeling of that pushes you forward when you speed up. Oh no, when you speed up you go back. When you put the brakes on you go forward. So that's that feeling of acceleration. So you'll have a question that asks about acceleration. The main thing you just need to recognize is you're going to have a function. You need to go to two derivatives, not the first derivative. First derivative gives you velocity. Second derivative gives you acceleration. So as long as you remember that, you'll just say, okay, this problem, they give me a position function, right? They call it the position function. That's really giving us distance. So that's what we're going to start with. And this one is from the exam review, so you'll see this. Straight line, that's fine. It's in feet, t's a measure in seconds, that's fine. Find its acceleration, okay. So that means I need two derivatives. So to get the second derivative, I have to take the first derivative first. And this is, again, where e to the t, it's an exponential, it's its own derivative. The derivative of 4e to the t is 4e to the t. Again, using the chain rule, derivative of t is 1, so that doesn't change it. That's its derivative. We took its derivative. But again, in your mind, you're saying, it doesn't look like I did anything. I just copied it. But no, I did take its derivative. We take the derivative of 8t squared. The 2 comes down, so we get 8 times 2 is 16, minus 1 from the exponent, t to the first power. Derivative of 3 is 0. So we did take its derivative. Okay, but we're not done. We need to take the second derivative because this is just going to give us velocity, which is speed. To get to acceleration, we take the second derivative. And again, 4e to the t, its derivative is still 4e to the t. The derivative of negative 16t is just going to be negative 16, right? T to the 0, which is 1, so there's our derivative. Now, if the question wanted the acceleration in terms of t, we're done, right? This is in terms of t. It's a formula. It's got the t in there. But this one gives us a particular value for t. T is equal to the natural log of 6. Natural log of 6 is just a number, but they have us plug it in that way. So what we need to find is the second derivative with the natural log of 6 plugged in. So that's 4e to the natural log of 6 minus 16. Now you could go ahead and plug that all into your calculator if you like, but if you understand a little bit about exponentials, you don't need to, but that e and natural log are inverse functions, so e raised to the natural log of 6 is actually just going to become 6. So we got 4 times 6 minus 16. 4 times 6 is 24, minus 16 gives us 4 and 4, it gives us 8. So our acceleration would be 8. But again, you could plug that, just plug it into your calculator, it'll give you the number 8. Okay? But just watch for those. It'll be something like this. They'll give you a function. They'll ask for acceleration. Just remember you have to take 2 derivatives. So it's mostly testing, do you know what acceleration is? It's the second derivative. The other way we applied the second derivative is dealing with concavity. So in any other function, if we take the second derivative, it will tell us the second derivative. If the second derivative is positive, it's concave up, because that's a smile, right? Some positive things make you smile. If it's concave down, the second derivative will be negative in that whole region, because that makes you frown. So that's what you're going to get tested on, is do you understand what the second derivative means? So questions like this, also along with it, they may put, and again, this came from the review, they may have the first derivative. What does the first derivative mean? Well, they're saying at -4, which is here, and 0, which is here, what's happening? What is the first derivative? It's the slope of the tangent line, right? So we can see at -4, oh, we got the slope, the tangent line would be 0. Okay, so that's that part of the answer. Second question starts asking about the second derivative. So is the second derivative at -4, is it positive or negative? Well, for that we're looking at what kind of concavity do we have here graphically. It's concave down, right? Actually, that's a further question, but we could identify, from the graph it's easier to identify that. A concave down is a frown, so what kind of a sign does it have? It has negative. So we can say at f of -4 will have a negative sign, a concave down. The second derivative at 0, it's over here. And again, this is concave up. And so that's a smile, which means it's positive. So the second derivative would be positive everywhere there. Okay. Inflection points are involved. What is an inflection point? It's where the concavity changes from up to down or down to up. And so since in this particular case, concavity, our second derivative has a negative, and then when it's concave up, it goes positive. How can you go from a negative to a positive? What do you have to pass through? You have to go through 0, right? Because that's, if you're going to change from negative to positive, that's the middle part. So if it has an inflection point at x equals -2, and you can kind of see that here, I guess that's about 1, 2, be about there, then the second derivative is going to be 0. Okay, so concave down, second derivative is negative, concave up, second derivative is positive, inflection point, second derivative 0. Okay, so just kind of know those things. And then we've kind of answered this. It's concave down from -infinity to 2, and then it'll be concave up on the other end. But know those things. Okay, so again, go through, do the review, Spend some time on the things you're doing well on. Go ahead and review them a little bit more, build that confidence. Focus on what you're struggling with. Go back to those section by section reviews if you need to. Go back to the lectures. That's the other reason why they're recorded, so you can watch those. Put them on a playlist and just sit, get some popcorn, watch it.
Quick question. The E just still throws me off sometimes, so I just have to like take a second to work through it. So like for this one,